So what we need is you are going to need to be able to draw with your protruded a 30, 60, 90 triangle, and I will show you specifically how to draw it right now. I'm going to draw the triangle in blue for no other reason than I've been told that it's more entertaining for you to have different colors on the board. Somehow it keeps you more engaged. I don't know how I feel about that. I don't think it's true, but whatever. Here we go. We have our 30, 60, 90 triangle. So here is our 30, 60, 90 degree triangle. Clearly you can see where the different angles are. This is our right angle. This is the 30 degrees. And this is the 60 degrees. What we're going to do is we know the index of refraction of air we've already identified as 1.000. The index of refraction of this particular block is going to be 2.50. And what we're going to do is we're going to send a ray of light into this triangular prism, and we're going to trace the ray diagram as the light goes through the rectangular prism. So this is going to be our initial incident light. In order to figure out what happens, we need to actually go through and do the math and draw the figure on the board. So this is our initial incident light, and it's going to be put in at a 90-degree angle or a right angle to the block air interface. So first off, what is our incident angle here? The incident angle for this particular example is, Danielle? So the incident angle for this ray of light. It is not 90 degrees, which is one of the reasons I go through this, because it is often confused as being 90 degrees, but it is not. It's important to know what this incident angle is. Not 90 degrees. You can tell me what the incident angle is. Nate? 0 degrees. How do you know it's 0 degrees? I guess I didn't. Interesting. Carolyn, well, how do we know it's 0 degrees? Remember, your incident angle, all of these angles are measured with the normal. I can't really draw the normal right now because this incident ray of light and the normal are going to be over one another. They are both at the exact same angle. Therefore, the incident angle here is 0 degrees. This incident ray is at 0 degrees relative to the normal. Now, we need to figure out, using Snell's law, what the refracted angle is. So we have the incident index of refraction times the sine of the incident angle is equal to the refracted index of refraction times the sine of the refracted angle. We have the incident angle, but I need to know what the incident material is and what the refracted material is. So we're going from, the light is going from air into the block. So Edward, which are the two materials? The air and the block. Which one's the incident material, which one's the block?
Air is incident, refracted.
Notice it's going from the air into the block. So the air is the incident material, and the block is the refracting material. So we have the incident index of refraction is going to be air. So we have 1 times the sine of the incident angle, which is 0, is equal to the refracting index of refraction, which is 2.5, times the sine of the refracting angle, which we're solving for. Class, what is the sine of 0? 0. So we have 0 on the left-hand side is equal to 2.5 times the sine of the refracting angle. In other words, 0 divided by 2.5 equals the sine of the refracting angle. Class, what's 0 divided by 2.5? 0 equals the sine of the refracting angle. In other words, the refracting angle is equal to the inverse sine of 0. Class, what's the inverse sine of 0? 0. In other words, this is something to be aware of. It doesn't matter what the refracting material is, or the incident material, as long as the angle of incidence is 0 degrees, the refracting angle will also be 0 degrees. It is going to be undeflected. So it's going to go straight through. So we draw it just like that. And again, what we're doing here is we are tracing the path of this light through the block. So what we need to do now is we need to draw our normal. And let's figure out what this angle is. Theta 1. Theta 1 is going to be our incident angle as the light leaves the block. What is the incident angle, theta 1, Justin?
It would be
Theta 1, we got to do some geometry here to figure out what theta 1 is. What? Talk to me. Give me anything.
well, it's your perpendicular there. Or up.
This and these two are both perpendicular, true.
Is it 90 on the right of theta 1?
Remember, this dotted line, by definition, is the normal, so that makes that 90 degrees.
And then
Abigail, help me out.
It's 180 on the side of the triangle.
This whole piece right here is 180 degrees.
That means that 90 minus that angle, it's the angle,
This one right here.
60 degrees.
This one is going to be 60 degrees because these two lines are parallel. Therefore, these are both going to be 60 degrees. Therefore, theta 1 is just
there's
30 degrees. You can also look at it this way if you would prefer. We know this is 60 degrees. We know then this is going to be 30 degrees because this is going to be a 30, 60, 90 degree triangle, and these are alternate interior angles. Either way, both give you that it's 30 degrees. We know theta 1 is 30 degrees. We're trying to figure out the refracted angle now. Again, we have the incident index of refraction times the sine of the incident angle equals the refracted index of refraction times the sine of the refracted angle. Now, what in this case, Julia, are the incident and the refracting materials?
Is it
They can't both be the same thing.
would the incident be the block?
Okay, why would the block be the incident one?
Because it's coming from the block.
It's going from the block into,
Is it going into the air?
it's going into the air. That makes the block the incident material and the air the refracting material. Notice that we've switched. When the light was going into the block, it was one way, and when the light is trying to go out of the block, it is reversed. So you have to be careful what's the incident material and what's the refracting material. So here we go. We have the incident index of refraction is the block, so that's 2.5 times the sine of the incident angle, which was theta 1, which is 30 degrees, equals the refracting index of refraction, which is 1 because it's air, times the sine of the refracting angle. We're trying to figure out the refracting angle here, Brian.
where again is that 2.5 from?
2.5 is the index of refraction of the block. Sine of 30 degrees. You've done a circle of
1/2.
unit circle, so this is 1/2. So we have then 1.25 is equal to the sine of the refracted angle. In other words, the refracted angle is equal to the inverse sine of 1.25. The inverse sine of 1.25. The inverse sine of 1.25.
You can't do that, can you?
That's a good idea.
Can't do that. Why? Abigail.
Sine can't be.
agree mathematically that's why. I'm looking for physics, right? That's the mathematical reason as to why it doesn't work. So physically, what's happening then? We tried to figure out the refracted angle. Thomas.
Is the light being reflected?
It's being internally reflected. This is an instance where it can't be refracted because it is totally internally reflected. Another way to look at it is to figure out the critical angle. We know the we know the sine of the critical angle equals the refracted index of refraction divided by the incident index of refraction. Therefore, the critical angle is going to be equal to the inverse sine of the refracting index of refraction divided by the incident index of refraction. In other words, the critical angle in this case is equal to the inverse sine of the refracting index of refraction, which is air, divided by the incident index of refraction, which is the block, which is 2.5, gives us the critical angle. Which is
23.578.
In other words, if the incident angle is greater than the critical angle, you have total internal reflection. Therefore, because theta 1, which equals 30 degrees, is greater than the critical angle, which equals 23.578 degrees, you have total internal reflection. Okay, so instead of having refraction, and instead of the light going out of the block, it stays in the block, and we have internal reflection, which means the light is going to bounce off and be reflected somewhere along here, and I need to know what is theta 2, the angle at which this light is internally reflected. The angle at which the light is internally reflected. Connie? What is angle theta 2? Theta 2. The angle at which the light is internally reflected.
Wait, I thought it was 90.
Well, the angle for the normal is 90 degrees, but I erased it so that we can draw a reflected, totally internally reflected ray here. Theta 2, give me something. Anything, it can be wrong. We'll talk about why it's wrong. I'm fine with that. I don't know isn't an answer. Come on, Connie. We got the light. We know theta 1 came in at 30 degrees. The question is, we've determined that it's not refracted, so it's reflected, and I want to know what angle is it reflected at.
Can we just go back to the 90?
Can't be 90 degrees because that was the critical angle. This is not, it's not going to be refracted via the critical angle. What is the angle that it's reflected at? Ms. Martin?
It's reflected at 30 degrees.
Why?
Because it's being reflected and the angle of incidence is the same as the angle of reflection.
Going all the way back to the beginning of chapter 14, the angle of incidence is always equal to the angle of reflection. Therefore, theta 2 equals theta 1. The angle of incidence is always equal to the angle of reflection. So I need to draw my reflected ray right here. It's going to go just like this. Unfortunately, it's going to go over my theta 2. Let me draw that, that's fine. It's going to go right like this. This is our refracted, or totally internally reflected ray, theta 2, 30 degrees. Now, I need to draw another normal. So I have my normal right here. I need to know what theta 3 is equal to. Theta 3. Stuart, Mr. Hensley, what is theta 3 equal to? Work me through it. I mean, you know this is 60 degrees. You know this is 90 degrees. Theta 2 is 30 degrees.
Theta 2 is 30.
So what's this angle?
That's 60, so that's a 60, 60, 60.
Correct. That makes theta 3.
Another angle at 90, so like theta 3 is 30.
Therefore, we know theta 3 is equal to 30 degrees. Therefore, what happens at this interface? Abigail, what happens to the light when it runs into the block air boundary right here? This is what we're learning today. We got to know what happens right here. Mega, what happens right here?
Is that where it's totally reflected?
Totally what reflected? Totally internally reflected. Is it totally internally reflected? Sandra? No, it is not, she says. Why is it not totally internally reflected, Sandra? What's your argument? You can if you'd like to argue that way. Why would it be? She's answered both questions, or both answers now. Yes and no, Mega. I need a why. I need to know clearly the why is what we need, not yes or no. Carolyn?
It
The ray is totally internally reflected because
because it's the angle of incidence is 30 again,
the theta 3, which is the angle of incidence, is 30 degrees.
and it's still going from the block to the air, so it still has the same critical angle.
Therefore, theta 3, which is 30 degrees,
It's still greater than the angle, the critical angle, which is 23.5.
therefore,
It is totally different.
totally internally reflected. Coming back to the definition of the critical angle. If the incident angle is greater than or equal to the critical angle, you get total internal reflection. Again, the incident angle is 30 degrees, which is greater than our critical angle, which is 23.578 degrees. Therefore, we have total internal reflection, which means the light is going to bounce back, reflect back this way. We're going to have theta 4. What is the value of theta 4? Filippo? I haven't drawn the line yet because I don't know what angle to draw it at, so I need to know what angle theta 4 is.
30 degrees.
30 degrees because?
Because one is 90.
You're not, I agree that this is 90, but that's not quite why theta 4 is 30 degrees. Why is theta 4 30 degrees? Bianca? It doesn't have to do with the fact that it's a 90-degree angle there.
Because it's the same as the reflected angle.
What are the same again?
The reflected angle is equal to the incident angle.
The incident angle, theta 3, is always the same as the reflected angle, which is, in this case, theta 4. Remember, the incident and the reflected angles are always the same. So I draw my reflected angle like this, at a 30-degree angle to the normal, like this. So now we have that ray, and we need to figure out what theta 5 is. Theta 5 is going to be drawn relative to the normal again, theta 5. What is angle theta 5? Benedict.
30 degrees.
Theta 5 is not 30 degrees. Theta 5.
60.
60 degrees. Walk me through it, Benedict.
Because the triangle in the left corner is 30, 60, 90.
This line and this line are going to be parallel. You can see that because theta 4 is 30 degrees. Therefore, this is going to be a 60-degree angle right here. That makes this a 30-degree angle. Therefore, theta 5 is, Benedict? 60 degrees. Because the 30 degrees, and we have a 90-degree angle right there because it's the normal. Therefore, we know because theta 5 is equal to 60 degrees. This is feeling slightly redundant. James, what happens?
It's totally
The totally is very clear.
totally internally reflected
Because
because it's greater than
what is it?
the A is greater than critical angle.
A ray is not an angle.
I mean incident.
The incident ray, theta 5, or sorry, the incident angle, thanks Jake. The incident angle, theta 5, is 60 degrees, which is greater than the critical angle. Therefore, we have total internal reflection. Therefore, I'm going to draw my reflected ray, theta 6. I need my angle, theta 6. Class, at this point, you should be able to tell me what theta 6 is. It has an angle measurement of?
60 degrees.
We'll try that again, class. 60 degrees, because the angle of incidence and the angle of reflection are always the same. Therefore, theta 6 is going to be 60 degrees. So I come up here and I draw my angle at 60 degrees. And I draw my ray. I'm just going to go like this. Now, I need to draw the normal again, and I need to figure out the angle. The angle right here, theta 7. Theta 7. What is the angle for theta 7? Brian?
30.
How do you know what theta 7 is 30? You know theta 6 is 60?
It looks like the angle above it is also 60.
Looks like. We need to know it is. Notice this line and this line are parallel.
Yeah, parallel.
Therefore, this angle is.
60.
Therefore, if theta 6 is 60 degrees, this angle is 60 degrees, what does that make this one? 60 degrees. Now, I'll tell you, you can't use it looks like, because chances are good when you do this on a problem on a quiz or lab, for example, it'll be something like 47.8 degrees, right? Then you actually have to walk through and figure out how to do it. So we have theta 7. We now know theta 7 is equal to 30 degrees. Tell me, please, what happens? Blackhurst. Theta 7, this incident angle, theta 7 is 30 degrees. Tell me what happens.
It is totally internally reflected, so it bounces on the side of the
How do we know it's totally internally reflected?
because theta 7 is greater than the critical angle.
Therefore, we have total internal reflection. And we need to draw an angle. Oh, theta 8. Let's see if you're still playing my game. Theta 8 class is equal to. Oh, class. Class, class, class. I know you're lethargic. Why are you lethargic, you ask? Because it's so hot. Don't you worry, it'll only get into 60s tomorrow. You've been lethargic all week. Mr. Palmer, I can't think, it's so hot. I'm sorry, you still have to think. Theta 8 class has an angle of 30 degrees. Because the incident angle is always equal to the reflected angle. How many times can we do it in a row? We will see. We now are going to draw it at 30 degrees. It goes like this. We have our reflected ray. What is the next incident angle? After theta 8, the next incident angle is, Justin. It is not 90 degrees. The next incident angle, unfortunately, is not 90 degrees. Stuart, it is 0 degrees. It gets back to that same problem. Remember, it's the angle with the normal. So this right here is parallel to all of these. It is normal to this surface right here, which means this incident angle here is 0 degrees. So what happens now? Kevin.
The incident angle is less than the critical.
Okay, so now the incident angle is less than the critical angle. Therefore, what happens?
Therefore, it's refracted.
We have, finally, refraction. Okay, what is the angle of refraction if the incident angle is 0 degrees? Class.
0.
0. We've already done it, right? We did it at the very beginning. We know the angle of refraction is also going to be 0 degrees. We already showed that. Therefore, I simply draw the ray coming straight out. And it turns out that if the incident ray is 0 degrees, the final ray coming out, the final refracted ray is also going to come out at 0 degrees, and the two are parallel to